Hi everyone, in this video I'm going to do a crash course in the statistics and probability topics covered on Algebra 2. So Algebra 2 has a good chunk of statistics and probability questions. They relate to statistics that is quite rich and quite complex. However, the Regents tends to ask about rather predictable and straightforward concepts. So as long as you know the basic definitions of these statistics, you can do well on these questions. So I'm going to begin on the reference sheet, and then I will work through problems that get progressively more complicated as examples. I'm using the June 2023 Regents as my source material here, but I'm using the updated reference sheet that will be used in June 2026 and moving forwards, because this reference sheet has much nicer scaffolds for statistics. Specifically, if you look at the bottom of the updated reference sheet, they have provided what they say the normal curve down here. This is what we call a normal distribution or a bell curve. In a normal distribution is just saying that we have a set of data where the mean or the average is at that center of the data. So most of the data is clustered around the average. This is how life typically works. Like the average is where most of the responses are. And this symbol here that is mu, it's a Greek letter, that stands for your mean. So the mean is at the center of the data. And then you can see that above and below, all of the responses are clustered towards the middle, but as you get farther away, they kind of tail out. They get less frequent. And this is why we call this a bell curve. So things like height or speed or a lot of data in the real world is what we call normally distributed. And normally distributed means that it follows this pattern. Most of the responses are towards the center around the mean. And as you get farther away, it becomes less and less common to have that response. The other key piece of vocab here is, so our mean is the average, sum of values divided by number of values. The key Algebra 2 concept is the standard deviation. That is this symbol here. So this is your standard deviation. What standard deviation does is standard deviation is a measure of how far the responses are spread out from the average. So what I mean by that is, let's say there were two different tests given. Maybe in the Unit 1 test, the average was a 80, and almost everyone achieved an 80. So maybe the data would look like this. Everyone was very close to an 80, very few people were above or below an 80. Versus the Unit 3 test, maybe the average was still an 80, but there was a lot more variability. There were a good number of people above the 80 or below the 80. What we would say is that in this second test, the standard deviation was larger because the data is more spread out. So standard deviation is a way of quantifying how far the responses are spread out from the mean. If the standard deviation is larger, the data is more spread out. If it is smaller, it is clustered closer together. What's cool about standard deviation is not just an arbitrary kind of like rating of 1 to 10. Are you far apart? Are you close together? Standard deviation can be used to calculate exactly what % of responses fall in a specific range. So I'm going to begin with 1 standard deviation and 2 standard deviations. What you see on this diagram on your reference sheet, you see this 34%, 13.5%. If I start at my mean and I add 1 standard deviation and subtract 1 standard deviation, that will give me a range that includes a total of 68% of the responses. So 68% of the data falls in this range, up 1 standard deviation or down 1. So for instance, if my mean was 20 and my standard deviation was 5, that would mean 68% of the responses were between 15 and 25, up 5 and down 5 from the mean. If I go a standard deviation again, so if I go up 2 standard deviations and down 2 standard deviations, then I get a range that, as a grand total, 13.5 plus 13.5 plus 34 plus 34, includes the middle 95% of data. So 95% of the responses fall within 2 standard deviations of the mean. And this is the concept that the Regents will very frequently ask about, is they're going to ask about whether something falls in that 95%. If it falls in that 95%, we call that a typical response. Like, that is an expected value. It is not unusual if you're landing in those 95%. If you're farther away than those 2 standard deviations, that's when you start to be an unusual response, because only 5% of people are going to be outside of 2 standard deviations. All right? So what we want to remember is the mean is the center. Standard deviation tells us how far we are. And if I go up 2 standard deviations and down 2 standard deviations, that gives me a range in which 95% of the data falls. Cool. So I may scroll back here, but let's apply this to a specific problem so that you can see an example. So in June of 2023, here is one example of a problem that asks about this concept. This problem says an app design company believes that the proportion of high school students who have purchased apps on their smartphones in the past 3 months is 0.85, or meaning 85% of students have purchased apps. A simulation of 500 samples of 150 students was run based on this proportion, and the results are shown below. So essentially what they did here is they have some kind of average, right? And then they ran this simulation many times to see how spread out the data would be. And then they give us this data. We do not need to look at the individual dots. What we care about is, we care about the mean. So we know, if I'm thinking of my bell curve, right? My typical result is 0.852. And then here it says standard SD. My standard deviation is 0.029. What that means is, if I go up, if I add 0.029 twice, and if I subtract 0.029 twice, that is the thing that's going to give me my 95% of the results range. Okay, so we'll see if we have to do that in a second, but my mean is 0.852. If I go up 0.029 twice and down 0.029 twice, that tells me where 95% of my results will lie. So they say, suppose a sample of 150 students from your high school showed that 88% of students had purchased apps on their smartphone. So we have our standard deviation here, and then we have an individual result, 88% of students, or 0.88. Based on this simulation, would the results from your high school give the app design company reason to believe that their assumption is incorrect? All right. What this is basically asking in disguise is 0.88, is that something that falls within that 95%, or is it outside of the 95%? If it's inside the 95%, everything is working like we expect. If it's outside, then it's unusual and we have cause to question things. So what we're going to do is we're going to calculate 95% of our responses, right? 95% of our responses, we're going to calculate where they lie. So I'm going to take my 0.852 and I'm going to add 2 standard deviations. And that is going to give me 0.91. So that's the upper bound of my 95%. Then I'm also going to take my mean, and I'm going to subtract 2 standard deviations. Minus 2 standard deviations. If I subtract 2, I get 0.794. What this tells me is 95% of the data is between 0.794 and 0.91, right? And then I'm just going to ask myself, so that's where the expected results are. I'm going to ask myself, is this individual result they gave me, does it fall in there? Yes, it does. 0.88 is between 0.794 and 0.981. So now I'm going to say 0.88 falls in that interval. And so these results seem correct. If the 0.88 fell outside of that interval, I would say 0.888 falls outside of that interval. These results seem strange. Doesn't mean they're wrong, but if they fall outside of the interval, they are unusual. If they fall inside of the interval, then there's no cause for concern. And no matter what, like, you can see in this question, the actual meaning of that is rather confusing. But the setup is always going to be find your 95% interval. Ask yourself, does this example fall in that interval or not? If it does, everything is normal. If it doesn't, you would say that falls outside of the interval, so something is strange. So let's look at another question. This one's bopping back to multiple choice that covers a similar topic. All right, here it is. Look, see how we have another bell curve? The minute you have a bell curve, you can assume that you are dealing with this standard deviation concept. Up to, down to is 95%. So Marissa and Sydney are trying to determine if there is enough interest in their school to put on a senior musical. They randomly surveyed 100 members, and 43% of them said they would be interested in being in a senior musical. Marissa and Sydney then conducted a simulation of 500 more surveys, each of 100 seniors, assuming that 43% would be interested in being in the musical. Their output is below. So again, you have this concept where we have a mean, we have an average, 43%, 0.43, and then they redid the survey a ton of times. Redoing the survey a ton of times is how you get lots of data, and then you look at how is that data distributed. So 0.43, that is we want to assume that is our mean, right? And on my simulation, 0.43 is around here, so that's roughly in the center. Then they ask, the standard deviation of this simulation is closest to. And notice they did not give us the full data set. We could look at these individual points and try to count them up, but they're not asking us to actually type these into our calculator and calculate the standard deviation. Instead, they're expecting you conceptually to be able to visually recognize what you think most of this data is. So if I look at this bell curve, right? What I want to remember is that if I have my mean, if I go up 2 standard deviations and down 2 standard deviations, that is where my 95% live. So if I'm looking at this data, I can see that most of the responses, they kind of taper out here, and they're kind of tapering out here. Right? That was not a precise science that I just did, but we can see that if I was going to call something 95%, 95% of my responses are in here, and then I have just these outliers on either end. If I look at this range, My mean is here. I put my upper bound around, that looks like it's like at maybe 0.53 or 4. And I went down to approximately 0.32 or 0.33. What this means is that I'm going up about 0.1. I'm going down about 0.1. If that's 2 standard deviations, that would be 0.05 plus 0.05. And it would be down 0.05, down 0.05. So we can see that just visually, I'm going up about, if I approximate like what 95% looks like, 2 standard deviations is somewhere around 0.05. Now looking at my answers, number 4 is a distractor because that is our mean. That is not the standard deviation. Number 1 is too small. If I only went 0.2, I would need to be able to fit 95% in like this range. That's not enough to fit 95%, too small. If I went 0.09, I'm going to end up like with a range that's too big. I'm going to have 100% of my responses. So that's also an incorrect response. So even though what I did is kind of an approximate science, this is asking us to visually recognize which of those numbers, if I add and subtract it from my mean, gives me that middle 95% interval. They're not telling you that this is about 95% interval, but if they say standard deviation, that your first question should be, are they asking me for the 95% interval? Are they asking me for usual, unusual? Then that's what I'm looking for. Up to, down to is 95%. The one other thing they can do with standard deviation is if your answer is not something that can be answered with 95%, then it means you're going to use a normal CDF. Normal CDF is very complicated mathematics. However, your TI calculator does it for you. So I'm going to read this example number 16. We're going to talk about why you can't do this with just 95%. So they say the heights of the students at Central High School can be modeled by a normal distribution. I'm going to just sketch my bell curve right away with a mean of 68.1. So I know that's my typical height. And a standard deviation of 3.4 inches. So if I go up 3.4, up 3.4, down 3.4, down 3.4, that's where I get my middle 95%, right? But before I bother calculating it, let's read what they ask me. According to this model, approximately what percent of students would have a height less than 60 inches or greater than 75 inches? And then looking at my answer choices, I have 0.86%, 1.26%, 2.12%, 2.98%. None of these are 5%. None of these are my even 95, which means I'm going to have to do something fancier than just get my 95% interval. What's really cool and powerful about standard deviation is standard deviation can be used to calculate the percent of any range you want. The mathematics behind it requires calculus, but all you are being tested on is whether you understand the concept. So on our, rather than showing my 95%, what I'm going to do is I'm going to keep my little diagram here, and I'm going to draw the intervals they asked me about. So they said students with a height of less than 60. So if this is 60, we want all of these students, or greater than 75. If this is 75, we want all of these students. So we want to figure out what percent of students fall here and here. This is what's called a normal CDF. So to calculate a normal CDF, what you can do is, notice that on your calculator, that button that says VARS, above it, it says DISTR. That stands for distribution. So that's where you can do things with distributions. So I'm going to click second, VARS, and that gives me my distribution menu. And then I'm going to choose the second option, normal CDF. So the way you type in a normal CDF is you type normal CDF So this is second vars. And then you kind of need to know what information it's asking for. What you need is the normal CDF is going to tell you the percentage of any interval that you want. So we need to tell it the minimum of our interval, then the maximum of our interval. Then we need to tell it the mean of the distribution. Then we need to tell it the standard deviation. So it needs 4 pieces of information. It needs what is the minimum and the max of the interval you're asking about, what is the mean of your distribution, what's the standard deviation, and it will spit back, 3% of people fall over there. For this question, we have 2 intervals that we're going to need to add together, so we're going to need to do this twice. So over here, I want people who are less than 60, so that means 60 is my max. For my minimum, I'm just going to put something that's arbitrarily low because I want everything below 60, so I want to put something tiny. I'm going to put 0. There's no one who has a height less than 0, so I'm going to make a really tiny number my minimum. So I'm going to say normal CDF of, actually let me just do it one more time, second distribution, normal CDF. I want the interval from 0, and then I'm going to use the comma button, from 0 to 60 if my mean is 68.1 and my standard deviation is 3.4. So again, I do minimum, comma, maximum, comma, mean, comma, standard deviation. Close my parentheses. If I hit enter, that tells me what percent of people fall in this range down here. So down here, that is 0.0086 or 0.86% if I move that decimal places. So I have 0.86% down here. Notice that's one of our answer choices. However, 0.86% is only the kids who are below 60 inches. So that is a distractor because we also want the kids above 75. So for 75, we want everyone, 75 is our minimum, and we want to go arbitrarily big. So I'm going to say everything from 75 to 1,000. Maybe someone's 1,000 inches tall. So you want, if you're trying to go on forever, you can't type in infinity, type in something unreasonably large. So I'm going to do this again, second vars, get my normal CDF. I want everything from 75 to 1,000 if my mean is 68.1 and my standard deviation is 3.4. So that upper group is 0.0212, so that is giving me maybe 2.12%. I have 2.12% up there, 0.86% down here. Why am I erasing? To get them combined, I'm just going to add those together. Not every question will give you 2 intervals. This is a kind of spicy one because they give you 2 intervals. An easier question would have just said what percent are below 60, and then you only have to do 1 interval. Here they gave you 2, you have to add them together, kind of a pain in the ass, but it's nice for a model problem because then you can see me go through the process twice. So 2.12 plus 0.86 is 2.98. That tells us 2.98% of students fall in those 2 intervals. So overall, with standard deviation, I'm going to go back to my reference sheet. What you can see is the questions may sound very complex, and they do relate to complex kind of higher level statistics. But your path to the answer just requires understanding the definitions. Your mean is your center. Up to down to standard deviations gives you 95%. If it's not asking about 95%, normal CDF. Nothing else will be asked to you about a standard deviation. So even if the story is confusing you, you don't really understand, if they're asking something about, is this usual, is this unusual? All they're asking is, find that interval, say yes or no about whether the thing falls inside of it. And these, like, you can see on this test, this was a 4-point question. So you can get, oh no, I lied. That was a 2-point question. But wherever it is, like, it's pretty complex. A lot of people don't get, like, we didn't get to this unit this year. But if you practice it a little bit, like, or at least try getting that interval, if you show the conceptual understanding on these, you often can get partial credit, even if you're a little hazy on the exact numbers. Like, all you want to show is that this tells me an interval where 95% of the responses fall, and does the thing they're asking about fall in there or not? That is statistics. Realistically, I actually think question 16 is less likely. If you are ready for the 95% interval, that is the most common thing. Question 16 is less common, but if you know how to do question 16, it's basically a calculator skill. It's just it is a little more complex. And that is all the statistics that they might ask. The other topic that they could ask about outside of statistics is probability. So probability will relate to two-way tables, frequency tables. However, it's going to take them a little bit farther than you may have done them in Algebra 1. In Algebra 1, we would just calculate what percent of students like chocolate or whatever. In Algebra 2, the basic concept is something that's called conditional probability and independence. So I'm going to read this question, then we'll use this as an example to define those terms. This says, a public radio station held a fundraiser. The table below summarizes the donor category and the method of donation. So looking horizontally, we have phone calls versus online. And then in our columns, we have supporter versus patron. I guess supporter and patron is different types of donors. Phone calls and online is different methods. And then everyone fits in one of those two categories. So you can be a supporter who was online, you can be a patron who was online, but everyone is divided up into those places. Independence, the concept of independence is basically asking, we have two different questions here, right? How did the person donate? And what type of person are they? Are they a supporter or a patron? And did they make phone calls or did they do it online? Independence is trying to use math to determine whether those two questions impact each other or not. So one famous example of this is, does running for the bus make you late? Does running for the bus make you late? So people are more often to be running to the bus if they are late, right? You're less likely to run for the bus if you're early. So running for the bus and being late are related concepts. We would say those are not independent. It doesn't mean that they cause each other, right? Like if you start running, you don't become late. It doesn't mean cause and effect, but it does mean that there is a relationship between those two questions. So here we might be wondering, if you were in charge of this, if you were in charge of this radio station, you might want to know, like, oh, does the phone calls versus the online, does that change what type of donors I end up with? That would help you make some decisions. So let's look at what they asked us to do. To the nearest thousandth, find the probability that a randomly selected donor was categorized as a supporter given that the donation was made online. So the minute you see that given, this is what's called conditional probability. Given that the donation was made online means we want to restrict ourselves to only the online data. We are ignoring the other data. So if I'm finding the probability that a donor was a supporter, given that the donation was made online, that means that online is my total. So online, in total online, I had 1,200 plus 2016. I had 3,216 online donors. Of those who were online, the supporters were just these ones. I'm not including the 400 because we restricted ourselves to the donors who were online. So supporters were 1,200 of the online 3,216. And then I'm just going to divide that. and round to the nearest thousandths. So the nearest thousandths is 0.373. In probability, we typically keep things as a decimal. We do not convert them to a percent. So 0.373 means that the 37.3% of the online donors were supporters. But we leave it as a decimal in probability rather than going back and forth with percents. That's what's called our conditional probability. It's not all the supporters, it's only the supporters who were online, and you have to figure out, okay, what's my total and what is the part of that total? Then they say, do these data indicate that being a supporter is independent of donating online? What we want to do now is we want to say 37.3% of the online donors were supporters. If we ignore the fact that someone donated online, if we look at all methods, does that change the percent or not? So what we're going to do is online probability that you are a supporter. Now we're going to look at, in general, is that the same or is it not? So in general, we had a total of 1,600 supporters. 400 plus 1,200. And in general, we had a grand total of 4,288 people. So if I don't restrict myself to online, then let's see what the probability of being a supporter is now. Look at that. I got 0.373 again. So the fact that I got the same probability of being a supporter, whether I paid attention to the online patrons or not, the fact that I got the same answer both times means that those two variables are independent of each other. Being online does not affect your likelihood of being a supporter at all, because it's 37% either way. If we did it in general and we got something like 50%, then we would say those are dependent events. The results of one affect the results of the other. There's a relationship, they're connected. But since we got the same result, whether or not someone was online, then we would say being a supporter is independent of donating online. The two questions don't impact each other. If the probability is the same either way, then these two things are independent. If it is different, then the two things are dependent. And that is conditional probability. So overall, what you want to think of in conditional probability is if you're given a given question, think of how am I restricting this table to only part of it. Then if you're asked about independence, compare that probability in the row to the probability in the big picture. If the probability changes, the things are dependent. If it does not change, the things are independent and they do not affect each other. And that is all of the stats and probability from this June exam. So there is I forgot one other one. You might get these questions about survey design. So something like the business office of a local college wishes to determine the methods of payment that will be used by students when buying books at the beginning of a semester. Explain how the office can gather an appropriate sample that minimizes bias. So in these questions, you want to think of these like common sense. And the keywords that you want to look for, if we are minimizing bias, then what we want is we want a random sample. We do not want to be picking our best friends. We do not want to only be picking students who like math. We do not want to only be picking students who are on the varsity soccer team. We want a random sample. So if they're saying explain how the office can gather an appropriate sample that minimizes bias, and the thing they are trying to study is determine the methods of payment that will be used by students buying books. You could say something like, the office could ask every 10th student in the alphabet how they bought their books. So then what this is doing, the office is selecting a sample of students. They're not asking every single student, but the way that they are selecting them does not allow any bias, because it is not, like for instance, something that would allow bias is the business office could just ask the students in the science building how they bought their books. Maybe science majors for some reason are more likely to use credit card than cash, or whatever reason. So you want to say, what is something that is completely random that still establishes a sample? It could be something like for instance, you would not want to say if breakfast is optional. You would not want to say survey every other student at breakfast, because then you're biasing students who wake up early in the morning. So you want to think of like, what is a method you could use to assemble a sample that is as random as possible and that you are not controlling the results. Sometimes this is in multiple choice. It's a little strange. It might feel odd. That's like, why is this on Algebra 2? But use your common sense. Don't overthink it if they're asking about survey design, and just do your best. If you want additional statistics practice related to these, just send me an email and I can, about which type you're looking for it, and I can point you in the right direction.